we can really elevate the understanding of our code or the behavior of different tasks, synchronous or asynchronous tasks, beyond those simple print statements. This is a dedicated chapter to this, to use OpenTelemetry. Some concepts that we need to understand: logs and traces. Logs are invaluable for recording events and errors in our applications, but they might not always offer a complete picture of what's happening. That's where traces come in. Traces capture the sequence of events across various functions and tasks, and that's where they can provide us with a timeline view of how operations interact and interleave. The second concept is OpenTelemetry. And OpenTelemetry is powerful. It's a powerful framework for gathering and analyzing telemetry data, including logs, traces, and metrics. It's designed to be vendor agnostic and open source, and that's why it's very widely adoptable. And by integrating OpenTelemetry into our Rust program, we can easily instrument and code to generate detailed traces. And the last one is the powerful visualization tool that we're using, Jaeger. And Jaeger can process trace data generated by OpenTelemetry and present it in an intuitive web interface. So I have to mention something that this chapter is a continuation of the previous process async chapter, that we had the data clustered into different groups based on their proximity, and then we calculated some statistics and transformation. But now I want to refactor this, and the key change is extracting the core data processing logic from the main function into a separate process function. Then the main function now handles the overall program setup, responsible for setting up the OpenTelemetry trace and any other necessary configurations. But anything else that we have before here for the statistics and all that goes to the process function, and this is our process function. And this function contains the core logic that was previously inside the main function. It takes end date and back until. This is our end date and back until the arguments of the function, which determine the time range for the data to be fetched. And it performs the following tasks. So fetch the earthquake data from the USGS API, combine results into a unified data structure, cluster the earthquake events, calculate statistics for each cluster, and then prints the results. In order to show you how tracing data flows in our application, I'll put together this diagram. And we've got different components that we break them down into steps. So we've got the tracing crate, we've got the tracing subscribers crate, and then we've got layers of formatter and tracing OpenTelemetry, and filter, a number of OTLP exporters, and then the data flows into Jaeger. Here. Now let's look at them step by step. Tracing crate. At the core, we're using the tracing crate, which is a framework for instrumenting Rust code. We insert trace points throughout our code using tracing macros like info, error, or custom spans. And then later we have the tracing subscriber, which provides a way to subscribe to the trace events emitted by our code. It acts as the central hub, collecting all the trace information. We've got the formatter layer. This layer within traces subscriber is responsible for formatting the trace data in a human readable way. And often we see it as log messages in our console output. Filter, which is optional, allows us to control which trace events are captured and processed based on environment variables. And it's useful for filtering out noisy or irrelevant data. And we've got tracing OpenTelemetry layer, which is crucial for OpenTelemetry integration. It takes the trace data from tracing and translates it into OpenTelemetry spans. So there are standardized units of weight that can be exported to various backends. So OTLP, or OpenTelemetry Protocol exporters, are responsible for sending our trace data to a backend system of analysis and storage. And this diagram, we have multiple OTLP exporters, indicating that we can send our traces to different destinations concurrently. And Jaeger is our chosen backend for visualization and analyzing the trace data, and it receives the traces from the OTLP exporters and presents them in a user-friendly web interface. How it works is, when our Rust application runs, the tracing macros generate trace events, These events flow through the tracing subscriber, where they're formatted and optionally filtered. The tracing OpenTelemetry layer then transforms the trace events into OpenTelemetry spans, which is sent to the OTLP exporters. Finally, the exporters deliver the traces to Jaeger, where we can visualize and gain insights into our application's behavior. At the beginning of our main program, we import some essential libraries. OpenTelemetry provides the core building blocks for OpenTelemetry instrumentation, and includes essential data types like key value, which we'll use to attach attributes to our traces. OpenTelemetry SDK contains the OpenTelemetry software development kit. It gives us the tools to create and configure a tracer provider, which is responsible for managing the collection and processing of trace data. The trace and resource modules are particularly useful for configuring traces and defining attributes related to our application's resources. Tracing library enables us to instrument our Rust code with structured logging in spans. These spans will form the basis for our OpenTelemetry traces, and tracing subscriber is actually the machinery for subscribing to the trace events, which come from the code. It includes layers, filters, and registers to help us control how the trace data is collected and processed. Here I'm going to show you how the trace data is going to be filtered and displayed in our Rust program. We've got the console in filter here. And in this one, a filter that determines which log messages should be shown in our console can be seen. It reads the configuration from the Rust log environment variable. This environment variable tells us to control or how to control how much detail we want to see in our logs. For example, if we set it to debug, we'll see more logging output, including debugging messages. If we set it to error, we'll only see error messages. If it's not set, then the default log level is info. And then we've got the console logger here. And this one is responsible for formatting the log messages and sending them to our console. And it uses the console in filter, this one. And this is just defined to ensure that only the messages that match our desired level of detail are actually printed. I showed you how to create a filter and use the filter for the logger. The next part is having this exporter. And why do we create this? Because it's important for sending our trace data to a backend system. And OTLP is an OpenTelemetry protocol exporter. And it's the standardized protocol that OpenTelemetry uses to transmit telemetry data like traces and metrics. And this exporter is how our Rust application will send the collected trace data to a backend where it can be processed and analyzed. And then you've got this part that you might be wondering what this part is. So this configures the exporter to use the tonic implementation of gRPC. gRPC is a high-performance open-source universal RPC framework, and is a common choice for communication between OpenTelemetry components due to its efficiency and reliability. By default, the exporter sends the data to this address, localhost 4317, but is customizable. This OpenTelemetry tracer pipeline is actually very essential, and it's got a lot of responsibilities. First of all, the responsibilities, I can say, creating spans. Whenever we use tracing info or decorate a function with the instrument attribute, the tracer generates a span. Spans record details about specific operations in our code, like the time it took, and any relevant attributes. The other responsibility is managing context. It tracks the relationships between spans, creating a tree-like structure to imagine nested functions that represent the flow of execution in our code. Sampling is another responsibility. Responsibility can intelligently decide which spans to keep and which to discard based on sampling configuration. This helps manage the volume of trace data. And exporting spans, it sends the collected spans to the exporter, which we'll discuss next. So with this next line with exporter, we connect our OpenTelemetry tracer pipeline to the OTLP exporter. And the next one is this part, which is the with trace config. and allows us to customize how traces are handled. We can set the sampling rate, how often traces are recorded, and add resource attributes to our traces. Then we have this key value new. This part adds a specific attribute called service.name to our spans, giving it the value we decided earthquake tracing app. Later on, this name will show up on the Jaeger web interface. So we can identify which service generated the trace data when we view it in the Jaeger later. Now we have finally the last line, install batch, that we install the tracer provider with a batch processor. This means the tracer will collect multiple spans together and send them to the exporter in batches. That improves efficiency, obviously. I showed how to set up for the tracing layer within our OpenTelemetry configuration. This layer is a crucial bridge between the tracing information generated by our ROS code and the OpenTelemetry ecosystem. Then we have tracing in filter here, which is similar to what we saw for the console, the filter that we define for the console. This filter is similar to that, but it specifically targets tracing information. It reads configuration details from the Rust log environment variable, and by default, the level filter trace is set, and which means all tracing information spans will be included unless you explicitly configure it differently in the environment variable. The next part that we have is tracing OpenTelemetry layer, which is responsible to convert spans generated by the tracing library into OpenTelemetry spans, and it acts as a translator between the instrumentation we've added to our code using tracing info. I will show that in parts of our code later, or the tag instrument attributes and the OpenTelemetry format. So where tracer connects the tracing layer to the OTLP or OpenTelemetry protocol tracer we created earlier. And this connection tells the layer where to send the converted OpenTelemetry spans for further processing and export. With filter, we apply the tracing in filter to this layer. And then we'll go to the next slide to finalize it. What we have here is combining all the components we've created and ensuring that the traces are correctly collected and exported. So we create a subscriber that combines our OpenTelemetry telemetry layer and the console logger layer. And this means that both tracing data, the spans, and the log messages will be collected and processed by this combined subscriber, by this exact one. And then we have set global default function that makes this combined subscriber the default for the entire application. This means that any tracing events, logs, or spans from anywhere in our code will be handled by this subscriber. This is how we make it global. And then we run the process function. We call this function, which contains the core logic of our earthquake data retrieval and analysis. Since the process function and any functions it calls are instrumented with tracing macros that I will show shortly, or the instrument attribute, the spans created within them will be picked up by the OpenTelemetry layer and sent to the exporter. And the last part is, so this is just an info, some sleep time, and at the end we shut down gracefully. There's just one thing left. So if we go back to this process function, as you remember when we refactor, we said the first element is the end time, the second element or the second argument of the function is back until. So we start from now, we go back in time, we retrieve the data and do the clustering and statistical analysis and transformation. Before running a demo, I want to show you how we instrument our application. So if we go in our code, the main one, we have tracing info in a few places and we have the log messages. So these are the log messages that we create. And the other way of doing it is in different files. We've got this instrument attribute behind the function, which means that we instrument our application to collect some spans. And then based on the setup that we've had, we send those traces or spans to our OpenTelemetry. And we can see this in a few places. In clustering, the RS, the Rust file, and also in statistics, you can see it. Now I'd like to run the application. So easy, cargo run, and then you will see some of the logs coming, and are different than the print statements. And you can see that it's coming at different times, and it's because it's happening asynchronous. It's not like a sequence of logs. And then the program finishes. I've got a Docker Compose here, and in this Docker Compose, you can always do Docker Compose up and set up your Jaeger. So the alternative is running Docker run, not using Docker Compose, but there's no benefit. And then we decide what ports we're using. You can customize it. And then when you run your program, then the traces and logs will appear on your web interface on this port that I'm going to. So here, well, we have two services. The default one, an earthquake tracing app that comes from our application. I define this as a service that I'm interested. You can say, just show me anything that happened in the past 30 minutes and find traces or any other times. So here you can see all the functions that we have, the instrument tag behind it, the instrument attribute. We have the traces here and how long they took. For example, this one took 18 milliseconds. And then with all the spans, you go to all the spans, 81 spans. And then all the details that this is calculate all cluster statistics async, calculate cluster statistics async, calculate metric statistics async, calculate metric statistics async. And this is exactly that tree-like structure that I was talking about. And you can see how long each of these little tiny tasks took place.